wonder if Jasmin just walks by. When you're ready. All right. Hello, everyone. Good afternoon. I'm Shahir, the Ankylosaurus, and the project that I've chosen involves generating functions. So let's get started. Consider the series A sub n, which is defined by Of course, we're going to try to get the enclosed form, and we're going to utilize the binomial theorem for that. For that, let's just write it out. We're going to multiply x n on both sides, and then we're going to sum it. So n 0. Imagine there's another sum here. Yes. And this side is going to, after we utilize the binomial theorem, 1 plus x to the power n, that's going to be a beautiful substitution. This equals 0, and choose a. As you can see, it's fairly close. We just have to do, hi Jasmin, one tiny thing. We just take the derivative. So x, and when you take the derivative, this becomes n times 1 plus x and minus 1. Sum stays the same. And choose k as a constant, so it stays the same. This k comes here, minus 1. One last step, we choose, we set x as 1. So if x is 1, we have n times 2 to the power n minus 1. All of this stays the same. Because x is 1, 1 to the power whatever, this just goes away. This whole thing goes away. And this looks exactly like that. So we substitute that in there, just after the substitution, this becomes 0. This whole thing becomes n times 2 to the power n minus 1 xn, and that is our closed form. Now, why should you care about this? I'm going to give you a practical example, some possible applications, and then we're going to move to the proof. So, what does this actually represent? So let's put some actual numbers on it and then see what we get. So let's consider n as 3. So 3, let's just have that as n. And we're going to represent that as 3 binary digits. So let's put all of the possible combinations. So we can do 0, 0, 1, 1, 0, 1, 0, 0. There we go, all of the possible combinations you can have, binary of course. And let's just say k is 2. So what does n choose k in this context actually mean? What that is saying is that out of all of the possible sets of 3 binary digits, how many of them have 2 ones in them? So let's see, 1, 2, 3, and there's 3 of them which have 2 ones, and if you, surprise, surprise, if you compute that, you get 3. Let's multiply the k, so n choose k times k. Now what does that represent? That says, out of all of the ones that have 2 ones in them, how many ones are there. So 1, 2, 3, 4, 5, 6, and of course when you compute that, you get 6. And then when you sum it, that tells you, so the whole sum, that tells you how many ones are there in total. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. And if you compute that, you get 12. And if you use the closed form and then put 3, you'll get 3 times 2 to the power 3 minus 1, that's also 12. So one possible application might be if you use this as a data structure, maybe you're making a game, you want to represent the ones as some event happening, and you want to count up at any given time how many of those events have happened. And this is sort of an easy way to calculate that. We're going to move to the proof now. Prove this equivalence using induction. Now the base case is almost trivial, but we're going to still write it out. Base, and we're going to set n as 1. So let's do that one first. So that's 1 times 2 to the power 1 minus 1, that is 0, 1, 1 times 1 is 1. For this one, because we're starting at 0, we're going to have 2 terms. The first term, because k will be 0, the whole thing is going to be 0. And then the second term will be 1 choose 1 times 1, which is 1. So 1 equals 1. The base case is proven. Now we're going to go to the induction step, because we can now say this is true for some n. Before we go to the induction step, we're going to use a fact involving Pascal's identity. And then it's not going to be apparent immediately, but we're going to use that later. So here's the fact. Correct. That's the fact. We're going to just put it there. And also, let me just write up the binomial theorem, which I erased accidentally. These two facts we're going to utilize in the proof. Now, for our induction step, we're going to prove that it's true for n plus 1 sum, where k is 0, k starts at 0, n plus 1 k chooses k, and there will be an n plus 1 here as well, and then plus 1 minus 1, that goes away. Now, this part right here, as you can see, looks exactly like this one, so we're going to sort of split it into 2 parts. So let's write it out. We're going to have n plus 1 sum is 0, and choose k times k plus other part. So n plus 1 0 and choose k. K minus 1. So we essentially just split this part into 2. This part, as you can see, is almost identical to our induction hypothesis. We just have this pesky little plus 1 right here. Now, if you think about it, n plus 1 is essentially the last term in the sum. And if we put it here, it's just saying n choose n plus 1. That's like saying you have 5 things, choose 6 out of them. That doesn't really make sense. So we define that as 0. And if the last term is 0, we can just ignore that last term and it wouldn't change the overall sum. Now we can substitute using our induction hypothesis. This just becomes n times 2 to the power n minus 1. And we just keep it at that. Move on to this one. This one we're going to use a bit of a trickery. We're going to define a variable j and set it equal to k minus 1. And then rewrite this in terms of j. So this is what we get. When k is 0, this becomes minus 1. It's n plus 1. So this becomes n stays the same. K minus 1 is j. And k becomes j plus 1. There we go. We just defined that in terms of j. Now, the only thing that's stopping us from expanding this is this minus 1 right here, because we're starting at negative 1. Again, kind of similar to here. If you think about it, if we start at minus 1, the first term is going to have minus 1 plus 1, so 0. So the first term will be 0. And again, if we then just ignore that and start at 0, it's not going to change the entire sum. Now we can expand this. So I'm going to move this just for the sake of board space. Not k. J equals 0. And choose j times j plus same thing. And j 0, and choose j. Here are our 2 terms. Now, if you notice, this one also again looks exactly like our induction hypothesis. So we're just going to write n times 2 to the power n minus 1. This one, we're going to come back to our binomial theorem and then use that to sort of do some trickery over there. If you set x as 1, we're going to have 1 plus 1 to the power n, so 2 to the power n. This part, because x is 1, 1 to the power whatever, it's just 1. So this goes away, and that looks exactly like that. So we're going to do substitution. This becomes 2 to the power n. Now let's collect all of our terms. We have 2 n times 2 to the power n minus 1s, and then 1 2 to the power n. So 2 n times 2 to the power n minus 1 plus 2n. Now it's some simple algebra after that. 2 to the power n plus 2 to the power n. And then when we take 2 to the power n common, we get n plus 1 times 2 to the power n. Now if you notice, this looks exactly like this. Thus our equivalence is proven, I guess. Let's see, I don't think I've missed any details. Yes, thank you for your undivided attention.
So is there a way that I can
Yes.
want to let you know, like, time-wise? Is it okay if I just leave my phone here and you just sort of glance at it? Or you want to take your phone, you can do that too. Just so you know, I don't want to interrupt you during your conversation.
I had the time here, but then I talked a bit too fast.
Okay. All right, thank you.